I'm just going to start by giving a brief introduction to motivate why you would want to use cloud for neuroimaging analyses. Ariel asked me to give a little bit of background about myself and how I got here, which may be interesting to some. My background is actually in computer science, and I decided I didn't care about computers and wanted to do something real. And so I transitioned to working on psychology and then neuroimaging, and spent the bulk of my career basically being a professor in the radiology department at the University of Washington, studying neuroimaging to look at longitudinal change. This is the last picture I took of my lab together in 2018 in the holidays. And what motivated me to leave this was that I started working on AWS specifically to try to understand how we could get around some of the problems I was having with scaling, trying to do more and more analyses quicker, faster, better, reproducibly, and realized that the cloud technology was exactly the right thing for that, except that it was difficult to use, and it was challenging to bring it to my lab. So seeing that we couldn't do that, I decided to jump ship and went to AWS and was there for 2 years working to help researchers use AWS. And then recently I just left for a startup, Ronin, that is really embracing that mission. And so what I'm going to talk about today really comes from my experience trying to bring cloud computing to researchers and still motivated as to why that is a really great idea. The traditional way of how researchers do neuroimaging is typically something like this. You buy a server that is quote unquote big enough for those larger analyses that you want to do. You get some time on a cluster, your university cluster, or national resources. You store the data wherever you have space to, and typically your university will have some scalable storage for you perhaps, but maybe not. And you just kind of cobble stuff together. But I think that this model is really untenable. Things are changing in neuroimaging, and we really need to think about cloud computing for this. And one of the fundamental reasons is that we just need more compute power. Algorithms have been becoming more and more compute intensive, iterative, needing specialized hardware, GPUs, things of that sort. More permutation testing is becoming standard in the field because of statistical problems with more subjects. And to store all this data, all of the products, all of everything that we need for that, and higher resolution data coming from better instruments, we need more space. When you start working at that scale, you need to share that data across institutions. And fundamentally, we all know that reproducibility is critical to this field, and that we need to be able to reproduce everything that we do. So this has always motivated looking at cloud computing. Just a brief overview of what I'm going to talk about. I just want to give some basic cloud infrastructure concepts. In this field, things are changing very quickly. So the specifics are less important than how you use them and how you think about these resources. I'm going to talk about what my vision of a cloud-based research environment should look like, and how you can think about preparing your workloads for a cloudy future. Think about the resources that are available and what you need to be aware of to move in that direction. And then my colleague Andrew is going to give you a tour of AWS specifically and show you these things in action. I am going to start with one of the basic concepts, which is the global infrastructure of a cloud provider. And I'm going to use AWS terminology specifically to do this because I know that the best, and I think because it's very comprehensive. The fundamental thing that you need to know about, and I'm sure Andrew will show you this in the console, is that you need to be aware of the region that you're in. So there's this concept of a geographic region where data are located and where your resources are created. Within that region, you want to have some sort of redundancy. And so for that reason, there are availability zones. And in each availability zone that you can choose, you have a concept of independent data centers. You're not necessarily aware of these when selecting where you put your resources, but what this means is that you have multiple data centers that are independent with respect to power, likelihood of failure. And so this gives you the ability to create infrastructure in the cloud and to use services in the cloud that are incredibly durable, incredibly available, incredibly reliable, far more so than if you have a disk sitting in a server somewhere at your institution with no copies, for example, right? So this is the kind of thing that you can put together, which is appropriate for storing data and developing platforms for collaborative projects. So, but fundamentally, the key thing is to be aware of where you're creating resources. Well, I want to talk about containers and virtual machines a little bit, because a virtual machine in AWS parlance is an instance, and those are the things that you create and deal with. Now, there is an upcoming, I believe, an upcoming lecture on Docker containers, which I think there was one that was co-located or co-timed with this talk. So you have a chance, if you don't know about containers, to learn about them. But the key thing is that there's sort of two ways to think about building modern infrastructure of this sort. And the first is a virtual machine, the second is a container. The difference, as you can see here in these two stacks, is that the containers do not replicate the guest operating system. So they're leaner, they're more efficient, they're smaller, there are other advantages with container technology in that you can describe exactly how they are built and version that. However, fundamentally, both of these are good stopgap measures for how to put together a reproducible workflow. If you've got a virtual machine, you know what's on it and you know what you're running. If you have a container, and I think a lot of people may be familiar with BIDS containers, for example, you know that that is a way in which people have packaged in the neuroimaging field many applications together and put them together in a way that can be reproduced. So, but I want to talk specifically a little bit later about some of the ways one thinks about containers and how we can use them more efficiently. But fundamentally, when you create a virtual machine, you're creating something that is reproducible as well. That alone is a good reason to think about cloud. This is just a non-AWS description of instance types that is not comprehensive or fleshed out completely, but it gives you the rough idea that one of the key concepts of cloud is that you have different types of machines that you can create. So here, for example, when you think about neuroimaging applications, you're probably thinking about needing more memory or needing a GPU, or maybe just needing a lot of compute nodes. And the point of this is that you get to choose with cloud infrastructure what kind of machine you want for purpose. And this gives you a lot of flexibility. This is probably one of the major reasons that one thinks about using cloud for compute, is to have this flexibility at hand. So this is just something to think about when choosing the architecture that you want. The problem with having so much flexibility, of course, is that you have to decide what you're going to run on. And this is one of the #1 questions that comes up for different applications across many fields. How do you select the architecture? The thing that I hear the most is, I used my HPC cluster, everything was installed on it. Now what do I do? So this is just my guidelines, my personal guidelines for neuroimaging on how to go about solving this problem. And what I think is a good way to think about it is probably one of the most, not always, but one of the most comprehensively compute intensive phases of neuroimaging is to do the single subject analyses. Your free surfer, your BIDS containers, all the single subject stuff. And that's what scales with the number of subjects. So what I think is a good approach is to pick the smallest instance type that you can generally get away with to process a single subject most cost effectively. This is a good way then to start small and test with a single subject. You can look at monitoring, see how much CPU and memory you're using as you run that. Do that a few times and get a sense for whether it's fitting within the bounds of the machine. And then I suggest speeding things up by trying to run many subjects in parallel on a cluster. I'll show you sort of roughly what that looks like. And if you can, and this is critical for thinking about the future, try to break up specialized types of processing into stages. So if you need a GPU for part of your compute, make that something you can run separately. Don't put that in the same script. Don't put that in the same workflow. And I'll show you why, because it ends up being far more cost effective in the end and is more forward thinking to be able to split those things up. But that's a good way to approach the problem. And you think about basically changing your computer to fit your compute needs. Let's move on to storage. So this is just some basic things about cloud storage. There are different options for different use cases. And these are just 3 generic types of options that different cloud providers will have different solutions for. So on the far left there, you have block storage. And there I'm talking about storage that is just more or less like a disk drive. And it's generally what is connected to your instances, your virtual machines, to provide the working storage that you use to actually compute against. Your temporary storage, your applications, your operating system, all of that stuff will be on block storage typically. You can also use that for databases if you install a database. There's an intermediate layer, which could be that a cloud provider can provide you a file storage. So you have a file abstraction for that. And that could be high performance. It could be scalable. So you may hear like Lustre as a potential high performance file system. You may hear, something that is a scalable file system. But basically what that will provide you is a file system interface that you can use perhaps across multiple machines, and it's sort of the in-between land. And then on the far right is object storage. This is where you put your data for longer term storage. So you would use that for keeping all of your DICOMs, your nifties, your original nifties, your products that you want to save, and largely because it is lower cost. And one thing I just want to mention about object storage is that since it is scalable and since you can continue to add stuff to it, that means that you're never having to take your data and put that on, a set of disks that are all far apart and hard to work with together. So one of the things that object storage that is really important for neuroimaging research that makes possible is the ability to put all of your data in one place together and be able to query it. I don't think that researchers think a lot about querying their data, sort of think more about writing scripts to go find stuff. But if you actually think about your data as a database, you can do an enormous amount of stuff with that. And so that is kind of one of the powerful things that, if I were to be thinking, as perhaps a lot of you are, about creating my lab one day, I would think about how to use object storage to be putting all of the stuff that I need together in one place and leveraging that in an efficient way so that I'm not wasting time writing scripts, finding stuff, and doing things. So the storage itself is incredibly as important, I would say, as the flexible compute. This is just a sort of a vision of what a cloud-based neuroimaging environment, research environment might look like. So here I have specialized clusters, one which is a CPU optimized cluster for running FreeSurfer. One is a GPU cluster for machine learning. Then I would have Jupyter Notebook handy, and I would have RStudio handy, and all of this would be on top of what I'll call a data lake, which is that big pool of data that's the object storage that can be queried. Those can be shared with other laboratories so that they can collaborate and put data there, and we could process it, that sort of thing. And that's sort of what I think this proliferation of different specialized types of computers for purpose, I think is a lot on some sort of large storage, I think meets the needs of many types of labs. One characteristic of compute clusters in the cloud is that they are elastic. And what that means is that they can grow and shrink to meet the needs of what has to be done with them. They can also have different types of compute nodes, so they don't all have to be the same type. They can be heterogeneous. But here's just an example showing how you may have a very small cluster when you're testing, and before an abstract is due, you go all out, you do all your subjects, and then when you leave on vacation, everything sort of shuts down. And then when you don't need any infrastructure whatsoever, you imagine storing your data on object storage, and it's there, and there don't need to be any compute resources if you're not working on the data. I want to show you this. This is the company that I moved to, Ronin, is dedicated to making things simpler for researchers. And I bring this up because I think that we're in a transition phase where people are learning how to make it easier to use compute resources, to use storage, together with all the things that functionally need to be there in a lab, like cost control, billing. You want to make sure you don't blow your budget. You want to make sure machines are shut off on a schedule, those kinds of things. You want to make sure data are secure. All of that is hard to build. And so I think that there are a variety of solutions that will be coming up to try to help researchers with that. So I bring this up to sort of give everyone hope that, in fact, it's not always going to look like going to the console and creating things from scratch, because as we learn how to do these things, we can orchestrate them. And so we can make them easier, and we can have design patterns for cloud computing for labs that look more natural and that fit workflow more readily. And Ronin is one, and I'll also show you another. And what I want to show you has to do with workflows as well. So everybody is familiar with how you do neuroimaging processing, and that you have typically a workflow which consists of multiple tools that you run. So that can be registration, it can be skull stripping, it can be aligning to standard space. All of these things have to do with, all of these things are different, typically run by different tools that you string together. They may be all different tools within a family, like you may use AFNI or FSL and use that family of tools, or you may put different tools together with other things because you prefer the way that, say, ANTS does registration, and you prefer the way that AFNI does single subject fMRI analysis. So you can assemble these things, and I think everyone has their own flavor of how to do that. But one of the characteristics here is that if you look at taking all these different tools and running them one after the other, to run this on a traditional infrastructure, one way to think about this is that you have to choose a computer, and that's that big orange box at the top that is big enough to run the largest tool that you have in that chain. So if, for example, if tool 3 needs a GPU, that orange box has to have a GPU. Another way to think about it is to create a compute resource for each one of your tools. What this allows you to do is it allows you to parallelize your workflow so that tool A and tool B, which clearly can be done independently of the tools 1 through 4, or at least tools 2 and 3, can be run they can be run simultaneously, and that might save you some time. This also gives you the ability to choose specialized compute resources for each one of these tools. And so if you think about a cloud environment where resources are coming and going, this model of thinking about things, having resources for specific units of compute, is far more efficient in the long term. So that is something important to think about when designing your workflows. So the basic pattern that you have here is that you've got some sort of object storage, longer term storage, and you want to copy the data that you need to use to your compute node, to faster block storage or file storage, and run your tool on it, and then take your outputs and put them somewhere else. This is kind of the basic compute thing, and the object storage that you use can certainly be the same. However, as you can see here with a workflow, it's a little bit more complicated to orchestrate. So you have a situation where you can have different types of tools that have different needs, as I described. Some can be compute intensive here, some can be memory intensive, and you want to put these all together. So in order to be even able to exploit that second architecture where each tool gets its own compute unit, you have to break them up. And this is one of the things that, for example, BIDS containers don't do. So with the BIDS container, everything is in one unit. It's using the container to encapsulate the entire workflow, which is great from a reproducibility standpoint, but not so great from a cloud efficiency or an efficiency standpoint. And this is something that I kind of feel that I want the field to be aware of as a whole. So let's talk about this separation of these tools and how they should run one after the other, and which can be done in parallel. We'll talk about that as workflow orchestration. And I'm just going to go through two options for workflow orchestration that are a little bit older. So some people who know me know that I have been on about Make forever. That was what we used in our lab, because basically 45 years of experience means you have no bugs. So you can be sure that the thing is going to run each time you want to run it. And that's really important to scientists, in that their workflow shouldn't be the problem after 5 years trying to make that go. But the drawback of something like GNU Make, which is still used a lot by bioinformatics folks, by the way, is that the syntax is really arcane, and it is really a pain to describe applications with complex inputs and outputs and how they should run. So for that reason, NightPipe is a solution that a lot of people use, and that's behind all the BIDS containers. And it's nice because it has a syntax that is Python based. But the drawback is, of course, that it is Python based, all Python based. So you have sort of a monolithic container, and it's a little harder to split up those pieces. And what's happened in the bioinformatics field is that each of those tools has usually emerged as an independent container, and they are put together by a workflow. So the kind of workflow that you then use, that you can use to put that all together, is something like Nextflow. And I recommend looking into this very, very highly, because it is its own language that allows you to put together pieces, snippets of code from any other language that you like. So if you've got a little Python thing, you can throw that in there. If you've got Bash, you can throw that in there. This Silas GitHub link is a lab that has really adopted this for Track2Flow and then all sorts of other workflows, but it's a good place to look. And this is just an example of showing you a little bit of the syntax for a skull stripping bet command. You can see that you're able to specify the inputs and the outputs and a little script, and you'll link these together. So all the bioinformatics codes in the world are really, really messy in terms of their inputs and outputs and how many files you get out and what their naming conventions are. And neuroimaging applications are exactly as bad, maybe worse. And so this language has support for those kinds of things, so that it's a little bit more elegant in the end than trying to wrangle that into something like Make. This is just an example of how you can string tasks together. And then let's see, and then the key thing is that this allows you to use containers very easily. So you can plop in your containers and specify here significantly the number of CPUs that you need and the amount of memory that you need. So what this gives Nextflow the ability to do is to then parcel out the different tasks to whatever resources are available, be it you're running on a single laptop or a cluster in the cloud or a cluster on-prem, or a native cloud environment that is optimized for running containers. So whatever you've got, you can do that. So, and I think that this sort of longevity and planning for the fact that you may have different resources at different times that look different ways, I think is pretty important in planning for the future in neuroimaging in the cloud. So that concludes what my prelude, and I think I will hand it off now, unless there are any urgent questions, to Andrew to give you an actual walkthrough of AWS.
Thanks, Tara. Hang on, just to break in here, there was one question from the audience. Somebody just wanted to clarify. Nextflow is, so David asks, to be clear, Nextflow is an alternative to Make and NiPipe, and I think the answer is yes, right?
Absolutely.
It's something you would use to write your workflows instead of Make.
Correct. Yep.
Okay.
Okay.
The floor is yours, Andrew.
Great, thanks very much. Hi, everybody. I'm Andrew Crabb. I'm a Senior Solutions Architect with the Academic Medical Centers team here at Amazon Web Services. My background, like Tara, is in computer science, but I come to AWS from a medical research career in research radiology at Johns Hopkins Medical School. So it's a subject that's very familiar to me and one that I enjoy very much. And so today we're just going to learn just some of the very fundamental services offered by AWS. We offer over 200 services. We're going to be talking about just 2 of them today. I'd love to talk more about it, but we have an hour, so we'll quickly go through this. This is a hands-on session, and the materials that you'll need for the session are in the Cloud-Computing channel. There's a couple of PDFs that I've posted in there. I'll just share my screen, and hopefully everybody is getting those materials. Okay, so there are 2 PDFs in there. One is this guide that I've got down the bottom left here. It's just going to describe some notes about a workshop hosted at AWS that we're going to run through today. And then the other one is where is it? Preview, here we go. These login links here. I've made 25 accounts, and I'm having 2 people log into each. You can each work independently. So that's the link that you need to click on next to your name to follow along. If your name is not on this list, just choose one at random and just jump in. You'll all be working independently. I've set it up such that actually up to 4 people can join each one of those accounts. The accounts will remain running for 2 days. You're very welcome to continue working through the rest of the workshop. There's more materials there than we'll be covering today. Obviously, please constrain your use to the running of the workshop. If you have any questions, please email me. Be very happy to work with you and help with any problems that you're having there. So today, 2 services. We're going to be using EC2, which is Elastic Compute Cloud. This is our fundamental compute server. This is what pretty much everything is built upon. So this is like a virtual server in the cloud. We'll be using it in a format where you can almost think of it as a server in the next room, and you're connecting directly to it. As you get used to cloud computing, we have a whole range of compute services. And as you adopt more and more of the advantages of the cloud, you can optimize more of those properties that Tara was talking about, the elasticity, durability, scalability, cost efficiency, all of these things as you gain familiarity with cloud computing and AWS, you can move away from using these basic services and move to something more specialized into containers, and then ultimately, if you're interested into serverless computing. So we're going to start with EC2 today, and we're going to be using Amazon S3. So this is object storage that Tara mentioned. Very interesting concept because this is different. This is cloud native. It's available essentially in the cloud only. You can think of S3 as an essentially unlimited storage medium that is accessed always through the web. So it's not like a disk drive in that you attach it to your computer. Everything is accessed through the web, and we're going to be using that today. Okay. So let me just have a look and see if people. Yep, I can see people logging in, so that's good. Just wanted to check that. So I'm going to borrow one of the links here. So this one here, and I'm just going to go through it with you. And I'm going to try and get through everything in an hour. So I may go a little quicker than people can keep up with, but the instructions are in the AWS General Immersion Day workshop, which is linked to. So the first thing we're going to do is log in. So you click on the link on the sign-in page, select the one-time password, the password-based verification mechanism, and that will send you a link to your email. And I think I'm on the subsequent screen here because I've done this before. And then you'll get to this screen on the right of my desktop, and we want the AWS console. Okay, you can always come back to this one here by entering the address that I've put in the PDF here, dashboard.eventengine.run. Okay, this information down here, if it is familiar to you, then you know what to do with it. This is your access tokens. If you want to log in with SSH to the instance that we're going to be starting today, we'll be starting a Linux instance today, but you don't need to. We're going to work through the console, so you don't need SSH access, but it's there for you if you want to use it. And then I click on log in. I'm already logged in under a different account. Let me do that again this time. Okay, so this is the full AWS console. You have access here to all 200 services that we're going to use, but you'll notice that the one on the very top left is EC2. This is our most fundamental service. So that's the one that we'll be using. If anyone runs into a hard error, please interrupt. Just let me know that, like, if nobody's progressing, then we've got a problem. But by the look of the logins, we've got certainly people logging in, and yep, that looks good. Looks like people are into the console. So we're going to work through a subsection of the AWS General Immersion Day. We're just going to be doing two parts of it, the EC2 and the S3 part. So I've made a couple of notes in the PDF handout of steps that we can skip or modify. So we're going to start here in the launcher web server instance. We're going to set up a virtual server in the cloud. We're going to connect to it, do some stuff, set up a little web server. There we go here. Okay, so we find our EC2 service. So you click on services and locate EC2, or if you want to find a service, I usually type it in. It's quicker than searching through 200 services. EC2 virtual service in the cloud. Just shrink that down. Okay. So this is the EC2 console, and it's telling us about how many instances we've got, how many of them are running, how many of them are stopped. Remember, as Tara said, that you can stop things when you're away. You only get charged while they're running. Okay, so we go to the EC2 dashboard, and then we're going to go to launch instance. This guy here. So the first choice that we get is the choice of environment, which in this case essentially means choosing the operating system we want to run. So this is called an AMI, or an Amazon Machine Image. So this is an image from which we're going to launch our instance. It contains the operating system, also the storage, networking, some configuration, and everything like that. So an AMI contains everything that you need to start up a fully configured instance. And you can create a custom AMI, we're going to do that later on, such that you can save the state of your instance and create a new instance directly from it. So we'll select that, Amazon Linux 2. This is just an AWS optimized version of Linux. And then Tara talked about choices. You can scroll down and you can see tremendous variety of different kinds of instances that we have here of all different sizes, and they're optimized for different applications. We're going to be using the T class, which is a low-cost burstable CPU general purpose instance, very cheap. T2.micro, we don't have the price on this page, but it would be cents per day, maybe 5 cents a day or something like that, 10 cents. So T2.micro, 1 gig of memory, 1 CPU, that's plenty for what we're going to be doing for now. So we're down here, we're on step 4, T2.micro, and then we'll go to instance details. Okay. Don't be overwhelmed by the console when you see it here. You're seeing the same console that users at any scale see. So you're seeing all of the options. So the vast majority of options, we can leave at default for now. And this is actually in step 5 here. We can skip this for now because step 5 of the workshop relates to a network that was set up in step 1 that we're not going to use. And so it's talking about network, subnet, and auto assign IP, and we're going to retain default, and enable. So you don't need to change anything there. So the network is already set up for you. Lots of options here. If you're interested in this, you're welcome to read up on it. There's a lot that you can do with an EC2 instance. On to step 6. For step 6, prefer method 2, copy paste. What we're going to do here, we're going to set up a startup script. So this is something that will run when the instance launches. So one of the key design tenets that we use at AWS is automation of everything. Because if we can start up one instance automatically, then we can start up 100 or 1,000. Or if one breaks down, we can replace it with another one. So one of the ways that we do that is by setting up a startup script. So this will provision the server when it launches and install any software that you need. It'll update the OS and do all that stuff for you. So let's copy the contents of the script here. If you know any Bash, this may look familiar to you. Basically, we are installing some software. We're going to install a web server. We're turning on the software that automatically starts services when we launch this machine, and then we're going to fetch a script and we're going to set it up as a web server. Okay, we don't need to understand this. That's just something that we're just going to copy and paste down here in advanced details. So we scroll all the way to the bottom, and then the user data in the advanced details, we're going to copy in the script here. So this will get run when our instance starts. Okay, on to step 7. We're going to add some storage. So here we can choose block storage that we can attach to our instance. So in addition to the object storage that I talked about that we're going to work with in the second part of the lab session, you can set up as much block storage as you wish. You have choices here as well, different speeds or storage that's optimized for different needs. Really interesting property of block storage is that it gets faster the bigger it is. So it's unlike a physical disk in that regard. Of course, this is an abstraction of the hardware that we're using. So we'll just stick with the defaults here. So what this is saying is that we're going to have set up a 8 GB disk of GP2 class solid state disk. And so that will be attached to our instance, just like a normal disk would. So we're starting up a server that's going to have an 8 gig disk. It's got 1 gig of memory. It's got 1 CPU. Okay. See some messages there. Okay, that looks good. Please just drop a message in the chat if anything goes wrong, and we'll keep on top of that. But it looks like people are moving along. Step 8 of the instructions, let me make that a bit bigger, is we're going to set up tagging. So this is another AWS thing, is that because you can potentially deploy any number of instances, compute resources, or other resources, we need a way to track which is which for billing, or to keep track of which are your resources. So for this, we use tags. So we go to add tags here, and we're just going to add a tag and give it a name. Name with capital N is actually a special, it's a special tag name, and it will be reflected in the name of the instance. I made a note here on step 8, just include your name because we're sharing accounts. If you added the same name, web server, custom AMI, then you wouldn't be able to tell which is yours. Like so, okay? And you can have as many tags as you like. You could have a tab, Crabb Lab. So you can set all these up. All of the resources that are deployed will have these tags attached, and these the tags will show up in the billing. It's also very helpful for automation. You can tag all of the instances of a certain type, or for a certain user, and then maintain them, administer them all at once. Security groups is step 9. So a security group is a custom, you can think of it as a firewall, which is attached to your instance, and it controls who's allowed to contact this from the internet. So bearing in mind the EC2 instance that we're creating will be in AWS, and so it has the potential to be addressed, to be logged into from anywhere in the world. So this is where we can restrict by IP who is allowed to reach and to attempt to log into our instance. So if you know that you're always going to be coming in from a certain IP, if you've got one machine connecting to another, you can put the IP number of just that machine in there, and then there's only one IP in the address in the world that can even get through the firewall. It can even attempt to log in. Or if you know that your institution, you're always going to come from a range of IP numbers, you would set that up here. So the way it's set up by default is we're going to allow SSH, which is the means of logging into an EC2 server. That's port number 22, and we're going to allow that from anywhere. So that's this CIDR range here, 0000. So that's the default for SSH. And we're going to add one. So we're going to add a rule. Remember, everything is blocked except for those things that we allow. And so the only other service that's going to be allowed to contact our machine is HTTP, because we're going to be setting up a little web server. So we'll add a rule. HTTP is always port 80. HTTPS is port 443, but we're going to be using HTTP in this case for our little trivial web server. And again, we'll allow it from anywhere. You'll notice that if you wish, you can select it to your IP number. That's my current IP. The only thing is that if your IP provider decides to change your IP, then you won't be able to reach it directly. You can come into the console and change it, or you can set it to a range, but we'll stick with anywhere for now. So this is just something to bear in mind. With AWS, we're very concerned about security, and we do just want to stress to you that if you do have your firewall address set up like this, then this is accessible from any IP address. So it's a good security practice to limit your IPs, and then we have layers of security on top of that. But for this class, this is sufficient. So we'll go next through to review. Any more notes? Okay. And again, it's just warning us that it's open to the world, that we can SSH in from anywhere. We've got a micro instance on CPU, 1 gig. We've got 2 ports open, 22 and 80, open to the world. And we click launch. Okay. Now, next layer of security is the keys required in order to SSH in. So go down to step 11. We're going to connect from the console. So for security, we're not going to install any keys on this instance. So I'll say proceed without a key pair. And we're just acknowledging that without a key pair, I can't SSH in. If you're familiar and comfortable with SSH, you can download the key pair and SSH in. But for the purposes of this class, we'll use the console. And we click launch. Okay. So now, if we go to the View Instances tab, we have created a server. It's this one here. You can start up more than one. And you'll notice that it's in an instant state of pending. So it's being provisioned, it's being set up within AWS. A lot of information here. Some of it's familiar with us. That's our availability zone, US West 2A, so it's based in Oregon. And then we have a DNS address, IP numbers. There's our security that we set up before, date and time that it was launched. So if you just highlight that, you'll get this information down here, and you'll get its public IP address. So a message come through. Okay, anyone having any problems?
So I had an issue where I couldn't launch this because it noticed that the name Launch Wizard 1 was used by a security group other than my own within the same VPC.
Ah, look at that. Thank you for catching that. This is what I did not catch by testing it on my own. As this is a result of having 2 people share an account. Thanks for that. The way around that is we would go to the instance, and let me go back to this step here. And it's actually very easy to overcome. We can go back here.
I overcame that by going back 2 steps and renaming it to Ariel's Launch Wizard 1.
Oh, there you go.
That it had a unique name, and then it was no longer a problem.
Even simpler, even simpler. Okay, so let me just catch up there. I'll start a new one. Instances, launch, AMI. That's the details. That's paste my startup script in there. Add storage, add tags. Thank you for catching that. Okay, 2 ways around this. Either just modify the name, or you could actually just create a new one, which would have the same defaults. So it would be this one here. Easier to take Ariel's approach, which is to modify the name of the security group. So thank you for that. Did that catch anyone else out? The new key pair option, it's if you're familiar with SSH keys, it's actually slightly different from that. This is a AWS specific one. Does it let you set up in the set up the keys in the host PC? Yeah, it creates a .pem file, a PEM file, which you can install into, if you're using PuTTY, or you say PC, so I'm assuming Windows, then yeah, it's the same concept. It's a public-private key. So you would download the keys, install the private key into your SSH client, and then use that to connect without a password. Alberto, did I understand the question correctly?
Yeah, the question was more because sometimes you have to, like, when you create the SSH keys locally, you have to copy one of the keys to the virtual machine or so this does all of this automatically.
Exactly. It copies the key to the instance that we're creating. Exactly.
All right. Thank you.
Sure. Okay. So yeah, that's a good point. When you get to the security group step, those who are sharing an account, which would be half or less of the people, just modify that the name of the security group. So something would catch me out testing it on my own. So there you go. Okay, let's go back to instances here. I'll start this one. And your instance should be running by now. Yeah. We go to EC2 dashboard, instance, and right. You see, I'm sharing my account. Well, actually, it's someone else's account. So this is mine here. And it's running. It's completed its startup test. So this is up and running now. Okay, so we go down to access the web service. And we get the information about the DNS address. And they say type, we can copy. Let's copy this public DNS address, or you can use the IP address. They say either, so we'll just copy that. Open a new tab, paste. Cool. So this is my server, and this is the web page that it's running. And you'll notice that it can even actually monitor what's going on. If you get onto this quickly, you'll see greater than 0 CPU load because the machine will still be busy from starting up. This instance ID here is used by a lot of services. This is a unique identifier to identify this EC2 instance. Mine is 5A84. That's me there, right? 5A84. Okay, so we have created an EC2 instance. Let's connect to it. So we highlight our instance here with the tick in the box there. Click on connect, and we'll use EC2 instance connect. So we have 4 different options. This one here, SSH client. This relates to if you're using the public-private key, then you could SSH in using those keys and in any client. EC2 instance connect is nice because we can do it all in the console. So we'll stick with that, and we say connect, and we're in. Like so. If you're familiar with Linux, you can look around, see what's running, see how much space I've got. Here is my my 8 gig disk that I started up. Here's my memory. Got 983 meg, got 1 gig of memory. So this is a Linux EC2 instance ready to do whatever it is that you wish. So in our case, we've pre-configured it to run a web server. Let's say that we had just installed a whole lot of software on here, more than we've just done. We put all this work into it, and you want to preserve the state of that instance so that you can clone it automatically, or you can distribute it to other users. So in this case, we've installed that software. We've installed the web server and the updated OS. So go down here to Actions. Again, we'll select our instance. It's mine 5884. Then we go to Actions, Image and Templates, and then Create Image. So that is going to create our own AMI. And they want us just to put in a name and a description. And you'll notice that it's got the same configuration as our machine because it saves all of that information. So it's not just the operating system, but it's all of the storage and the networking and everything like that. And then we click on Create Image, which I'm going to scroll across to get Create Image. Okay. And so you can now, oops, I beg your pardon, I did. Oh, okay, I did fill in an AMI, just didn't follow the instructions. Now, if we go to the left of our Ec2 console, we look at AMIs. Okay, there's my new machine image. It's being created. It takes a minute or two. Once it's finished creating, I can now launch another instance directly from that AMI by selecting it when I go to launch another instance. And the other instance doesn't have to be the same size. I could launch an instance of any size from that AMI. And I'll do that. I go to Ec2, launch instance, choose your AMI, and now instead of quick start, I go to my AMIs. Okay, it's not yet available, it's still creating, but that would appear here. And then that would be exactly the same as the one that we followed when we chose the Amazon Linux 2. So we launched one of these, then we modified it, we installed some software on it, and then we took an image of it, we store that, and when we can now use that, you can distribute it to other users in your lab, or you can use it yourself. This is frequently used if you're using more than one instance. You could have what we call an auto scaling group, something that where you're performing a large task that requires more than one instance, and the auto scaling group can deploy as many of these as you wish. They're all exactly the same because they're all started from the same AMI. And then you can terminate it if you wish, or you can leave it running. If you want to follow the rest of this workshop after the hour's up, welcome to go through and run through all of this. You'll notice little architecture that they've set up here. We're not going to do this all in the 1 hour, but what they're deploying here is they're setting up servers in 2 different availability zones. Tara talked about high availability. They set up a server in Northeast 2A and Northeast 2C, for example, such that you now can combine those 2 servers together into one and have a highly available web server, such that if either one of these suffered an outage, that your service would continue to run. So our example is a little simpler than that. We're doing just one instance in one availability zone, but you might find it interesting to walk through the rest of that lab. Okay, any questions? Okay, we're going through this at a bit of a trot. This is cloud computing done quickly. Let's look at S3. S3 is really interesting because S3, like I mentioned, is cloud native. So this is not the same sort of thing that you have on your computer. And so what you're accessing in cloud computing, we call a service or a highly available service. So it's not like you've got just one disk there that you're connecting to. There is something back there. There is an entire infrastructure whereby your data is duplicated, verified, checked, continually backed up, and it's distributed over multiple data centers. And in fact, in S3, there are 6 different copies made in at least 3 data centers, such that it has been calculated, and it can be mathematically proved, that the durability of an object, which is what we call files in object storage, is 11 nines of durability, or 10 to the 12 durability. What that means is, let's say if you stored 100 million files, 10 to the 8 files in S3, you could expect to lose one file, one of those 100 million, once every 10,000 years, once every 10 to the 4 years. And then in another 10,000 years, you could expect to lose one more of those 100 million objects. So extreme durability and low cost are 2 of the most compelling use cases for S3. So this tends to be the center of most AWS solutions as we put data in S3, and all of the services come to that. This is another sort of tenet of cloud computing, is we bring the compute to the data. Rather than bringing the data to the compute, we keep our data in one place, and then we deploy our compute services like that EC2 instance that we saw. We deploy the compute instances to use the data that's in S3. The container that is put inside, it's called a bucket. It's merely a concept. We don't create them like we create directories. You're limited to 100 per account. A bucket has no limit as to its scale. We don't say infinite, but there is no limit. There is no practical limit to how many objects you can put in one bucket. So you will certainly not reach the that constraint at all. How do we use S3? We find the service as we did for finding EC2, and S3 being very commonly used will be under your favorites here, or you can just type in S3. Okay, so here's a list of all of the buckets that belong to my account. So we'll connect to S3, and then we'll create a bucket. A bucket name has to be globally unique. As I mentioned, you don't have a limitless number of them. The intent with buckets is that you have a small number per user. You can have one bucket for an entire corporation. So we don't run out of bucket names. So bucket names are globally unique, and they have to be compatible with DNS, which is to say something that would appear in the address bar of your browser. So that means lowercase, underscores, dashes. This is actually incorrect. This is 63 characters is the limit for the length of a bucket name. So we'll call it immersion day. Something like that. Something that's unique. So frequently, people will use their login or some other identifier for all of their buckets just to give you your own namespace in the internet. And so that then if you start all your buckets with say your name or your lab's name, your identifier or something like that, then you can name it however you wish after that. And you are much more likely to find that no one else has used your bucket name. So we deploy a bucket in a region. Tara talked about regions. You could reach your bucket from anywhere. You deploy it in the same region in the interest of having your data nearby, being able to get to it most quickly, and it's also the cheapest if your compute and your storage are in the same region. But we're talking about global scope here. So we'll select our region, and we're going to use US West 2. You can deploy in any other region. So if you're working on behalf of somebody else in Europe or Australasia or anything like that, you can create resources for them as long as you're entitled to, as long as they've authorized you. And we just go create bucket. There probably wasn't another one called Immersion Day Andrew, but I just added some digits on the end, just in case someone else named Andrew had run this Immersion Day lab. Okay, now we've got a bucket. Buckets don't cost anything. You just pay the standard class that we have here. There are different classes of S3 buckets. 2.3 cents per gigabyte per month is the storage charge for the essentially limitless durability and limitless scale of that bucket. If you're storing data long term, if you're required for regulatory reasons, or if you've got source data, in my case, it used to be medical imaging scans, the raw data that came off the scanner. We have storage tiers that we refer to as cold storage tiers. You hear Glacier is a term used for that. They can be extraordinarily cheap. They are 20 times cheaper than S3. There are restrictions upon them. It takes a while to get the data back out of them. There is an egress cost. But it's often very valuable if you're required to keep your data, 5, 10, 15, 20 years, put it into Glacier, forget about it, and it just stays there forever. Has the same durability, the same 11 nines of durability as the standard class that we're using here. So this one costs a little more because of the convenience of being able to get to it originally. Okay, we're going to create an image file. So just click on that. Oops, right click on that. And we'll go save as. So download the image file. It's aws.ping. I'm going to save it in my downloads folder, and there's already one there. So I'll just replace it. Okay. Create an index.html file. So we're going to create this. Now, what they don't say is use a text editor for creating this. So not a word processor, and I've noticed in Mac, not, what was it, Notepad, I think it was. So if you have a favorite text editor that you use for your Python coding, just create an index.html. I will create mine. Because I'm old school. I'll do mine on the CLI. Okay, and now I've created a file on my local system called index.html. So they just want you to create a plain text file, just like that, no formatting in it, stored on your local file system. Okay, we're going to upload our aws.ping file to S3. So we'll go back to the console, back to our bucket. And this one is easy because it's just like in Windows or the Mac, we just click on upload, find a file. So we go to add files, locate your aws.ping file. Here it is here, and upload that. Okay, and it's succeeded. So far, this looks much like working from a file system, okay? Other than the upload bit. It kind of looks as if we've got files and folders. It even says files and folders, and we've got what looks to be a file here, and it is a file, but we treat it as an object. And one of the ways in which it differs is that this object has a unique address on the internet. So this is its address here. I beg your pardon, the HTTPS, this one here. So if we're using it through HTTPS, it has a URL that is guaranteed to be globally unique because our bucket name is globally unique because AWS would not allow us to create a bucket that was the same name as someone else. So this URL here is the web URL of that object. So this is different from a file system. This is why we call it an object storage system. So we upload our file. Well, what's step 5? Check the file information, click upload. Okay, so we upload our file. So here's our bucket, and it has one object in it. Step 6, check the URL information and select copy the object URL. Okay, so we're going to highlight that object. Actually, we might have to go into it. Oh no, here we go. We just highlight it. We say copy object URL. You could do it here, or I can click on this object here and I can copy that. Step 7, we will, right. Where did I put that note? I think the handout I gave you may have been a little out of date. I beg your pardon. The handout I gave is just missing a couple of notes here. In step 7, on the right of my screen here, do paste in the image URL. So just skip the second bit. So where it says ALB DNS name, don't worry about that one. That's the second one. So we're just going to do the first one. So we're going to edit our index.html file in the same editor that you used before, and we're going to paste in the URL of the object. So I am assuming that most people are in this course will be familiar with a text editor. I'm just going to do mine on the command line here. You can use your favorite text editor. And so what we're going to do here is within the image source, I'm going to paste in a URL like that. So if you've ever done any web development, you'll recognize this is an image tag. And we're going to say this is the source of our image, and the image source is the HTTPS address of our aws.ping, which is stored in S3. Okay, so I'm making a few assumptions here about editing this file. Is this okay with everyone? Anyone stuck here? Okay. Okay. So now we've got an index.html file, and we've added in the address of our own image file. Everyone's file is going to be called aws.ping, but the name of your bucket is in there. So that's what makes that unique. Okay, and then we skip the second bit here, that second box. Okay, upload the index.html to S3 following the same instructions as we did. All right. So we go back to our bucket, upload, locate your index.html, which we have already modified, and then we upload that. Actually, another interesting thing about S3 is that we don't modify files in place as we did with a file. We either send it to S3 or we pull it back. So any modifications are done locally, and then we re-upload the new version. Just wondering, there it is then. There's my aws.ping file. Okay, so now we've got two objects in our bucket, the index file and the aws.ping file. Onwards. So now we click the object that we want to see and we can look at the properties there. And you'll notice that by default for security, every object is owner only or private. So we have to grant permissions for people to use this for anyone to access it. You might have noticed before I clicked on the public URL for the aws.ping file and that opened up in this tab here, and I got a security message saying access is denied because every object by default is private. So we're very careful about stressing this to users is that by default buckets are private, by default objects that we upload into those buckets are private. If you make an object public in that bucket, it is public to the internet. Okay, so these are small sample files, so we're going to make these ones public. Your own work, you would probably be more careful. You'd follow the published guidelines about how to securely share the objects that you want. If it's a public website, then yes, you make it public, you make the resources public. But your own work, your data and so forth, you keep that private. It cannot be accessed by anyone else other than those to whom you give permissions. Select the permissions tab in the bucket. So go here. And we open the permissions tab. And then we go to block public access. And by default, it's turned on. So we've blocked all public access. We click edit and we just uncheck that. So that's step 3, uncheck the box. So now we have removed the block of all public access for that bucket. And just to be sure, type the word confirm to confirm that we are making this bucket public. So again, only data that you intend to be public to the internet goes into a public bucket. The majority of your data will remain in private buckets, and you can control access to it there. But we're making a website here. We want people to be able to see it. Okay, but now the bucket itself is public, but the objects within it are not. If I try to view this ping file now, still getting an error message, okay? Because the objects themselves are also private. So what we do in step 5, click on the Objects tab, highlight the objects here, and then under Actions, make public. Okay, so now we're making the objects public within a public bucket. Click on Make Public. And now that object is public to the internet. So for example, let's see what happens. If I go to view that index.ping file again, the aws.ping. Which tab was it? It's that tab there. Okay, so now I can see it. I had to make the bucket public, and then I had to make the object public. We've also made our index.html public. So that's what we are going to do in step 7. I'm going to copy the object URL of the index.html. Okay, so this is our web page. So what we're looking at here is the unique web address of our index.html file, and it is hosted within, font's a bit small probably for you to see, but it's hosted within my immersion day bucket. And you recall that I had to make not only the index.html file and the image file themselves public, but I had to make the bucket public as well. You click on an image, it's redirected. I clicked on that and I got access denied because I've done something wrong. Did I paste in? I think I pasted in the wrong information. I was trying to talk and edit at the same time.
I think it's missing the DNS to the AWS instance.
Yeah, I pasted in the .ping. Let me go back here. Hopefully somebody else was following the instructions and not following me. Oh, thank you. Right. Yeah, we don't have the active link. Sorry about that. We don't have the active link because we're not following the full workshop, and it's the load balancer itself, which was created in an earlier step, has an HTTP address, right? So that's this bit here that I told you not to fill in. Right. That's why I broke. Sorry about that. I'm trying to do two things at once. If we had followed the earlier step and we had a DNS address attached to this image, then we could click through to it. But that was done back in step 1 that we did not complete. All right. So with that exception, we have a working website here. We've got an image that's got a link. You click on it, you follow the link. The link is currently inactive because we did not complete the full workshop.
There's a question here in Slack. David asks, can plain text files be edited once uploaded, or do I have to re-upload?
Yeah, really interesting question. This is the thing about web objects, is that they are immutable. We don't open them in place as we do with a file. So because they're accessed through HTTP, we fetch them from S3, modify them, and then we re-upload it. And it's always as an atomic object. So yeah, the short answer is you have to re-upload. And in fact, I think we'll be doing that. So yeah, you fetch it, modify it, and re-upload it. So objects stored in S3, outstanding for static assets, images, data, something like that. For something that's going to be modified very frequently, maybe a word processing document you're working on, that is a less suitable use case because that's something that you're going to be wanting to open a lot. So for a web page, a static asset, something like images, CSS files, JavaScript files, and so forth are perfect. Things that you want to modify more often, you can fetch it, modify it, re-upload it. That's a less ideal scenario, but it's certainly perfectly valid. Okay, we got just 2 minutes, so okay, we'll go on here. Static website, and this one doesn't add too much here. There is one thing that I'd like to show you, and you're welcome to work through the rest of this lab. after the hour is up is that to move an object, for example, we will create a new bucket. And then once we highlight an object, we can move it to a new location. So this is all within within S3. So you can follow that section of the lab to move an object to another location. And then in the last minute that we have, another interesting property of S3 is that you can turn on bucket versioning. So this keeps backup copies of your objects. So when we upload an object, or if we delete an object from S3, that we've got a stack of objects underneath, and we can always refer back to previous versions. So we select a bucket, we go to properties, and in bucket versioning, we can say edit, and we just turn it on. And just like that, now, if we delete an object from our S3 bucket, or if we upload one, we can always access the previous version. So if you like, complete the lab or work through it from the start. It's a lot of interesting stuff there. If you'd like to learn any more, please do get in touch. I hope you really enjoy using AWS.
Thanks, Andrew. That was great. Let's see what questions do people have at this point about things that were presented so far. It's okay. We'll do one last bit here before logging off. Tzvi, do you have a question?
Yes, please. I was wondering about customized Amazon images for neuroimaging or how to create such images, if that's possible.
Yeah, it's a great question. Thanks for bringing that up. Actually, there is an Amazon machine image that is really great for neuroimaging applications, and that's one called the Nitric CE, the Nitric computational environment. And what's nice about it is it comes installed with a variety of software that you might want for neuroimaging. I think it has like stuff like FSL and FreeSurfer already installed in it. So I'll sort of maybe I'll look for it. Let me go into AWS here. Let me share my screen and I'll sort of show you where you find it, how you would look for it. So when you start an EC2 instance, at this stage, you could go and you could look for Nitric. And then it'll tell you there are some results in the marketplace. And this is it. The Nitric computational environment comes pre-configured with all kinds of neuroimaging data analysis applications. So there's a light version here as well. And there's even one that's specifically for the Human Connectome project that apparently comes with the Human Connectome project pipeline. And then if you choose that, then that is when you come to the point where you're, we'll see what happens here, but when you come to the point, okay, I see there's sort of an issue with the marketplace here. So for these accounts, that will be a problem. But later on, for example, for the hackathon, we can get you access to an allocation that has more permission. So if you'd like to play around with that, we can definitely give you access.
And that has both a version where you have the repositories to install the required software, the installed software, and then some data. So that's the 3 versions.
Yeah, although data you probably want to get from somewhere on S3, which is what I'll show next.
Just the Human Connectome project, I guess.
Oh, I think this is probably not equipped with the data for the Human Connectome project. I doubt that it has the data, because the data is accessible through S3. And sort of a best practice here is not to store it on not to store all of the data at once on one machine.
Yeah, that makes sense.
Where likely, if you're analyzing the Human Connectome project, you're going to want to analyze subject by subject first and then combine later on. So you want 1,000 different machines, each one working on one subject.
The human connectome data is available on the AWS Open Data program. So if you just search for AWS Open Data, it's just aws.amazon.com/open data, and just search for connectome. And so that data set is available for you. It's in S3, and so you can import it into your instance and work with it there.
And that's what I can show you next, how you would do that using a Python API. So that's sort of the next two steps. But before we go to that, what other questions do people have? Anything so far? All right, so maybe I'll jump in here, and I'm going to turn to something slightly different, but that connects well with things that you've seen so far by going to our Jupyter Hub. So you can go to that through the link on Sparkle, or you can type hub.neuroacademy.org, and that should put you in something like this. And so I'm going to go to the curriculum folder that you should all have and click on cloud computing. And then in here, there is one notebook called Reading Data from the Cloud. So as this notebook mentions, one of our major use cases for using cloud computing is computing on very large data sets, or data sharing, sort of another kind of thing. And what I'm going to show you in this notebook is a way to access data that is stored in Amazon's, for example, as an open data set in one of these through the Amazon Web Services Open Data Program. So what you saw here that I sort of clicked through quickly is the registry of the open data program on AWS. So AWS hosts multiple interesting data sets. I'm going to do this. You can see it's all kinds of data sets. The Common Crawl is a crawl of the internet. Sentinel-2 is a satellite that's monitoring the Earth. So this is kind of like remote sensing data of the Earth, and so on and so forth. There's lots of different data sets here. Of interest, there are a few data sets that are neuroscience data sets that you might be interested in exploring. So for example, the International Neuroimaging Data Sharing Initiative, INDI, have their data sets there. All of Open Neuro is the Brain Initiative archive for human neuroimaging data. And so all of Open Neuro is on S3, and I'll show you in a couple of cells down, I'll show you how to access data from Open Neuro. And then there's others, Allen Brain Observatory, the Human Connectome project that was mentioned is accessible. The Human Connectome project is accessible, but it will require you to get some additional credentials. So I'm not necessarily going to demonstrate that now, but if you are interested in Human Connectome project data, it's really actually quite straightforward to get the right credentials from the Human Connectome project so that you can get data in the way that I'm going to show now. There is in our data showcase, resource showcase, there is a video that Noah made about the Human Connectome project showing how to access that. At any rate, the library that I'm going to use is a Python library called S3FS. So one of the nice things about, among the many nice things about cloud computing is the fact that all of the cloud computing providers, the system itself is built as a big computer program. You can think of it actually as one big computer or an operating system where there's really just one computer that implements that operating system, and it is that cloud provider. And because it's built that way, that means that you can use software in order to interact with it and automate things. So there are application programming interfaces to do pretty much everything you can do by clicking on buttons in the console, you can do by writing Python code. So S3FS is one aspect of that. It takes advantage of that. S3FS stands for S3 file system. The idea is that we want to treat the S3, the simple storage service that you just saw, as a big file system. In this case, we're going to use an object called an S3 file system object. and we're going to set anonymous login as true. So we're going to access resources that anyone can access and access anonymously. We don't require particular credentials. If we were accessing, for example, the Human Connectome project, we would have to give our credentials in here. That's where we would enter our credentials. But in this case, we're doing it anonymously. For example, we can read a list of the files that are inside of this openneuro.org S3 bucket. So this is an S3 bucket at openneuro.org that contains all of the data in OpenNeuro, in the OpenNeuro archive. And you can see there are 607 OpenNeuro data sets. We're not going to look through all of them, but let's look at the 10 first ones. So here's the 10 first data sets, the S00001 and so on. The first 10. I mean, just to demonstrate, here is all of OpenNeuro. So it's the bucket contains these kind of subfolders, one per data set. So it's a lot of data. For example, let's look at this data set. Just to reiterate the syntax a little bit, when I created this object here, FS, this object behaves a little bit like a local file system on my machine. So I could call things like ls. It goes to S3, it gets the listing of the files inside an OpenNeuro, and it gives that back to me. And same here, when I call it, for example, on a subfolder of this bucket or sub-object of this bucket, it gives me the listing of the files that are in there. And this is organized as a bids data set. There's a data set description that would tell us what is this data set. There's a README that also tells us similar things. There's folders, one per subject, and then some other bids related folders. So for example, here I'm reading. So here I'm opening the file using this file system object, reading the file, and then decoding the bytes in there so that I can print it as a string. And this is a note that says that this data set was previously accessible as this other data set and was uploaded due to privacy considerations. I guess there was a problem with this data set and they fixed it, and now it's called 002596. Okay, that doesn't tell me much. We could go to the OpenNeuro website. And maybe find this data set on the public dashboard if we want to get a sense of what this data set is, who contributed it. There is pain control by co-adaptive learning. So it's related to paper. Here are the authors. Here's again the data. But we're going to try to access that data using software instead. So here's what we have for a single subject. We have two files in anatomy, two folders, an anatomy folder and a functional folder. Inside of the anatomy folder, we have a T1 weighted compressed nifty file, and we're going to get that file. So fs.get gets that file from its remote location here on openneuro.org. This is the data set, this is the subject, this is anatomy. And so this follows the breadcrumbs of what I did up above here, and it copies it into a local file called sub01 T1 weighted nifty.gz. And that takes a little bit of time, but once I do that, you can see that I have the file right here. It's been saved onto my local machine, and now I can read it using nebabble in this case, in Python, get the data and display the data right here. So this is to demonstrate that using S3FS, provided that we know the location of this file in the cloud, and provided that this file is openly available to anyone. The owners of this bucket did what Andrew was showing you before. They set the bucket to be public. They set every object in the bucket to be public, and so everyone can access it. You could have gone to in through here and click through a bunch of operations here to get the same, download the same file. But it's neater if you can do it like this, because then you can reproduce this activity. You can also write a little script that analyzes subject number 1, and then another run the same script on all 19 subjects to get all of their data. If you have a very large number of subjects, you can parallelize that in a way that resembles what Tara was showing in her presentation, and so on. So thinking of Amazon Web Services or any cloud service as a big computer that you can write programs for can be really beneficial, a beneficial way to think of the cloud, because that then allows you to automate things and scale them and so on. So that was the little bit of addition that I had on top of the presentation. And this notebook is available in the curriculum folder on the hub. If folks are interested in exploring these ideas or other ideas related to cloud computing, I'd be happy to have that be part of the hackathon next week, maybe combined with other things that you'll see later on in the week. Okay, let's see, what questions do people have about this? Okay, questions about anything at all that you saw? I see there is a question in Slack. Right, so there are a few questions here. There's a question about running Docker images. You can run Docker in AWS, and then you could build in AWS. There are actually a service to automatically build Docker images in AWS, and then provide those as in what's called a container registry. Pull those down into machines and do things with that. I can talk a little bit further about that if you'd like. A postdoc named Adam Ritchie-Halford, who works with me, wrote a little tool that I will share with you because it's a neat little tool for this kind of stuff. I wouldn't say small, actually. So this tool called CloudNaut is specifically written for operating, for doing large-scale computing on a service called AWS Batch. So AWS Batch, the idea behind AWS Batch is you create a Docker image that encapsulates your computation, and then you run that on multiple machines in parallel. For example, you might run, one of our examples here is, let's say that you're running some kind of image processing on MRI data. Here's a function. It gets as its input a subject identifier. And so here in this data set, there are only 6 subjects. It gets the data here. It's downloading it using even more simple-minded approach than the S3FS approach that I showed you. And then it runs down here. It runs some processing, and then it returns an FA image. And the idea behind that is that you send this function as a Docker image. You send this function to AWS Batch, and it runs that on a list of inputs. You give it as a list of inputs all the subjects you would like to run this function on, and then it runs that in parallel for you. So definitely there are tools to scale and do a lot more complicated things. And then Alberto asked, so if we wanted to use another bucket, we would just replace the name of the repo. If you wanted to use another bucket, for example, in what I showed, if you wanted to use another bucket in the open data registry, you would replace, let me show in my notebook. You would replace where I wrote openneuro.org. Right here, I did lsopenneuro.org instead. If I did, let's find another one like Indy. Yeah, I know, I happen to know this one. FCP Indy instead. Now I have as a list the data that's in FCP Indy. So inside of data, there are projects. So now you see these are the data sets that exist in FCP-ND. They include the Healthy Brain Network data set. They include Abide and other things that are the Rockland sample and so on. These are all data sets that are all stored together in this one big thing. And all I did is change the address here. And now I can do the same thing that I did down here. Download some data, do some processing, some analysis, and then maybe even in the end upload to another bucket, upload the results to another bucket. It's pretty typical.